Okay, so I'm Laurent Fesquet. I will chair this session. I will give you a short view of Sebastian Trimpe. Sebastian Trimpe is a full professor at RWTH Aachen University, where he leads the Institute for Data Science and Mechanical Engineering since May 2020. He did a lot of researches and he focuses on fundamental questions on the intersection of control, machine learning, networks, and robotics. Before moving to Aachen, Sebastian was at the Max Planck and Cyber Valley Research Group leader at the Max Planck Institute for Intelligent Systems in Stuttgart, Germany, where he keeps a side appointment at present. Sebastian obtained his PhD degree in 2013 from ETH Zurich with Rai Fellow d'Andrea at the Institute for Dynamic Systems and Control. Before, he received a BS degree in general engineering science in 2005 and an MS degree, a diploma engineer in electrical engineering in 2007. I noticed that he has also an MBA in 2007 too, from the Hamburg University of Technology. So we have also several awards like the Triennial IFAC World Congress Interactive Paper Prizes, also the Klaus Tschira Award for Achievement in Public Understanding of Science, the Best Demo Award of the International Conference on Information Processing in Sensor Networks in 2019. And he also got the same year Best Paper Award of the International Conference on Cyber Physical Systems. So a very active researcher, as you can see. And so it's time for you, Sebastian, to deliver your talk on event-triggered learning.
Thank you very much, Laurent, for this nice introduction, and thanks a lot for the invitation to give this plenary lecture. It's a great pleasure and honor for me to be able to do this. I don't see anyone, I only see my slides, so in case there's a question or anything happens, Laurent, please feel free to just interrupt me. So I'm very happy to be here at this venue and be able to give this plenary lecture because I've been following this conference for ever since it started. So actually in, I think, 2015, the first edition, I was already participating, and back then we were presenting our research on event-based state estimation at the time. And what I really liked about this venue is that it clearly shows that this idea of event-based algorithms or event triggering is very relevant in many domains. So in control, communication, signal processing, also vision. And in the last couple of years since then, we have been working a lot at this intersection between machine learning and control. And we also discovered that the idea of event triggering is also very powerful in this area. So I'm very happy that we can basically add to the domains where event triggering is relevant the aspect of learning and to present to you our research on or recent research on event triggered learning. So in this work, we are looking at the question essentially of when to learn. And this is particularly relevant when we talk about learning in the context of physical systems. And so before I go into detail about our work, let me set up the stage and give you the general background of what we are interested in. So in my group, so I guess the videos aren't playing. Let me just go back. Just 1 second. Okay. All right. So in my group, we are particularly interested in developing learning algorithms and AI algorithms for physical machines. So here you see some of our recent examples. On the top left, we use Bayesian optimization for automatic controller tuning that allows this robot to learn how to balance a pole. On the top right, we use Gaussian processes to learn dynamics of this model race car. In the bottom row, we show how we can use neural networks to approximate model predictive controllers while retaining the guarantees of the MPC. So in all of these works, we are connecting learning algorithms to physical systems. And when you do this, there are some particular challenges that you face that are different from what you have typically in machine learning. So when we look at basically where are the main success stories of machine learning and AI, these are typically in artificial or virtual worlds, like playing board games, playing computer games, or in simulation. And on the other hand, we still today don't have the general purpose robot that can tidy up the house better than we can, that can just help us in everyday tasks in the real world. So that brings about the question, like, why these differences? So one clear difference is that the robot, as well as the other physical systems we work with, are existing in the physical world, and they interact with the physical world. So the robot perceives the physical world through its sensors, and it acts in the physical world. So there's a close connection with the physical world. And that is not the case here, where here essentially the computer is playing a game where also nothing can go wrong. And that, of course, has some consequences when we talk about learning in the physical world. So one clear difference is that this system here can essentially try out new behavior, arbitrarily often, and this way generate lots of experiences that it can then learn from. And this is a key to the success of deep reinforcement learning, that you can try out a lot. The same, however, is not possible on our robot, because the robot making one wrong decision could already have disastrous consequences, like the robot being destroyed or someone next to the robot being injured. So clearly we cannot just try out arbitrary behavior on our physical systems. So this means one challenge when we talk about learning in the physical world is that we have the sampling is constrained by the physics, and compared to the complexity of the real world, high-dimensional and continuous state spaces, we also have often the situation of having relatively small data compared to the complexity of the problem. Another core challenge has to do with the fact that the systems, the physical systems, are not specifically built for solving just a learning task, but they are typically built for something else, for solving some other control task. So a production plan, for instance, is there to produce parts, but not specifically for learning. Still, at the same time, we want to do learning in some sense in parallel. So we also want to leverage the data during operation and do learning in parallel. And this brings some fundamental challenges, like, for example, should I keep doing what I already know how to do, or should I explore, try to learn new things in order to maybe get better on the long run? Furthermore, when we implement these algorithms on physical systems, we also have to deal with limited resources, such as embedded computation or also limited energy on embedded platforms. Another challenge comes from the fact that we typically don't just deal with one system, but we have many systems, like cooperating robots or vehicles in a platoon. So there are several decision and learning problems that are coupled to each other through the objectives of the dynamics, for instance. And there's not just one learning problem, but there's multiple coupled ones. And finally, because these systems exist in the physical world, we should better have an idea of whether they work or not. So in other words, we need guarantees about these algorithms to work well and not be dangerous, for instance. And these are particular challenges that we face when we deal with learning in the physical world. And these are fundamental challenges that my group is making some contributions towards. Now, in this talk, I want to focus particularly on one aspect, which is an aspect of the fact that we have to kind of learn in parallel to the systems being operational. Now, that by itself is nothing new either, because in classical adaptive control, for instance, that's exactly the problem that we're trying to solve. We're trying to learn and adapt parameters or controllers while we also solve our control task. Now, we are going to take a fundamentally different approach than what adaptive control does, because in adaptive control, you're trying to do both at the same time, continuously adapt your parameters, while we will argue that it can be beneficial to separate the two. So we will decide basically when we need to learn. So we will build triggers that let us decide when it's a good time to learn and update a new model. And that's what we're going to call event-triggered learning. We're also going to touch upon this aspect here, distributed systems, because we're going to show that these ideas of event-triggered learning, we can also beneficially use in network control systems. So essentially, we can build them on top more commonplace event-based control algorithms, put event-triggered learning on top, and then we'll see that we can save even more network resources in this way. And finally, when we develop these triggers, we want to give some sort of guarantees in the sense that the triggers will trigger at the right time. We're going to look at some statistical guarantees for this. Okay, so now let me give you some motivation for why I think it is a relevant question to ask, like when to learn. So if you think about a production plant, like these robots here or any other production plant, these are built to basically, these are built for non-stop operation. So you don't really want to stop them. So if you have to change anything or if you have to try something new, that's not what you want, because this will cost money. So you only want to do this if it's really necessary. And also changing anything in the system can also be risky, because any engineer knows the term never change a running system. As soon as you change something, there's also chances that things might not work as you expect. On the other hand, if things change, if the dynamics of your process change, there's wear and tear, etc., so the plant doesn't operate optimally anymore, that's when you want to learn, that's when you want to update. So the critical bit is that we need to detect when we need to learn. Another motivation are resource-limited platforms like embedded wireless devices, like wireless sensor networks, for instance. In these systems, basically computation and also communication is at a premium, so you only want to use these resources when necessary. And of course, you need resources when you do learning. When you do learning updates, you might share models across the network. So really, you want to only learn when necessary and otherwise save resources. So in both of these situations, the key question is when to learn. And this is the question that we're going to address in this talk, and we will aim at developing triggers that allow us to also give some sort of guarantees. Now in the following, what I'll do, I will first explain our general concept of how we think about the event-triggered learning, and then I will make this concrete for two specific problem instances. Okay, so first the general concept. So what we will be looking at here primarily is learning of models, learning of models from data. So this can be, for instance, some sort of a model learning procedure or system identification procedure. And obviously models are commonplace anywhere in engineering. We use them for all sorts of things. So we use them for simulation, for instance, or to do control. So whenever we have a model, there's a certain outcome that we have in mind that we want to achieve. So for instance, if you do simulation, you want to have low prediction error. If you do control, you want to have good control performance. And of course, now what is the outcome here? What is the result here will critically depend on the quality of the model. If you have a very accurate model, then you will have a low prediction error here. If you have a poor model, then you cannot expect to do any good here. So clearly, how the outcome is will critically depend on the quality of the model. Now, the core idea is to actually look at what is it that we have here in reality, to observe kind of how well are we doing, and then close the loop. So if we see we're not doing well here, we're not happy with the control performance, then let's go and get a new model. Now, of course, this by itself isn't a new thing, because that's essentially what we do when we put control systems when we implement control systems in practice, because we go maybe with a model-based design, then we try it out on our system, our robot or so, and then more often than not, we will find, okay, the initial design isn't good, and then we'll go back and refine our model, etc. But that's, of course, done in a very ad hoc manual way. And also there's other approaches like model-based reinforcement learning or iterative learning control, where you close this loop essentially in each iteration. In each iteration, you update the model. Now, of course, if you think about it, there are situations where learning also involves a certain cost. So this could be computation cost, this could be storing a new model or sharing a model across the network, which is something we're going to look at later. Or also the data collection could be costly in the sense that you might have to deviate from your nominal operation to excite your system to get rich enough data. And also, as we said, changing things always involves a risk. Never change a running system. So therefore, we don't want to change the model all the time, but we want to develop principled decisions of when do we need to learn. And that's what we're going to call event-triggered learning. So this is the main feature here, or the main concept, that we're going to look at certain criteria that we care about: control performance, communication rates, etc. And based on how well we are doing here, we're going to decide whether our model is okay or we need a new one. All right, so this is the general idea, and we've developed this for now for two basically concepts, or for two frameworks or two settings. One is optimal control. This is what we're going to look at next, and then we have network control. And I'm going to talk about both of these to explain you like what are the concepts that we have developed and how does it work, these triggers. And if time permits, in the end, I would also say a few words about some ongoing research where we look at kind of the core underlying question, which is similarity of dynamical systems and how should we compare dynamical systems. All right, so let's start with the optimal control. So here I again have the overview that I had before. So we have our model here, and this is what we do with the model, and here's our outcome. And we're going to look at the standard, the bread and butter optimal control case, which is the linear quadratic control. So in this case, we will have a linear system here, a parametric state space model, and we're going to have a quadratic cost, this one here. So that's just a standard LQR problem. And of course, what we care about in LQR is that we want to minimize this cost here. And we're going to use this cost, and we're going to basically, given a model, we can estimate, or we can compute like what cost we expect to see, and then we will compare this cost to what we actually observe in experiments. And if needed, if the two mismatch, then we will trigger a learning experiment. And learning here will mean that we do a system identification to essentially get new A and B matrices. And potential cost of learning could be on the one hand computation on embedded platforms, or also excitation, because you might have to use persistently exciting signals or specific signals to get rich enough data to then identify the A and B matrix, which might mean that you need to deviate from the nominal operation. Okay, so this is what we will do. So let's have a look at the details. So we have just the standard stochastic linear system in discrete time, and this is the quadratic cost that we want to optimize. Now what we can do is, given a model, we can actually compute what is the expected value of this cost. So this is just standard control theory. We can compute the expected value of this cost using Lyapunov or Riccardi equations. This will essentially tell us, okay, what is the cost that we expect to see if this model is actually the true model. And then what we can do to also is, in experiments, we can gather data, we can gather the X and U trajectories, and then just compute this cost. And then we can compare the two. Then we can say, okay, let's look at kind of a moving average, for instance, or some subsampled average of the cost that we see in experiments just from the data, and compare it to the expected cost that we expect to see based on the model. If the two match, that's an indication that the model is actually good. The model is good, it achieves what we want to achieve, namely the cost. If the two deviate, if the cost in experiments or empirical cost from data differs from what we expect to see from the model, that indicates that the model isn't good. Now, what can we say about this trigger? So in principle, this trigger, there's two reasons for why this trigger can fire. One is because there's a mismatch between reality and the model, because the model isn't actually accurate, so therefore we see a different cost in the experiment than we expect to see, and that's the case that we want to detect. But it could also be because we have a stochastic system that we're just unlucky, and basically we trigger due to noise, and that is undesired. So this essentially are false positives. So we trigger even though there is no model mismatch, and that's what we want to avoid. But we can do this using essentially standard concentration results that allow us to bound the probability of false triggers. So if we use Hoeffding's inequality in this case, for instance, we can give a probability that for this quantity here, which is the trigger fires even though the model is accurate, and we can bound this probability with this confidence level eta here. So using Hoeffding's inequality allows us to bound the probability of false triggers, and that then allows us to build these triggers such that they trigger with very high confidence. There are, however, critical assumptions that we have when we use Hoeffding's inequality. One is that for Hoeffding's inequality, the random variables need to be IID, need to be independent, identically distributed, and that is clearly not the case here because we're looking at a moving average of the cost, and these will clearly be correlated. However, we can mitigate this effect through some subsampling, but I'll get to this point in a second. And also another critical assumption is that Jn is supposed to be bounded, which of course isn't true in general because the cost might go unbounded for unstable systems. Nonetheless, we can try this trigger, and here is a simulation example. So let me walk you through this and explain this to you. So what we see here is basically these are just samples. This is the time index k, and this here is the trigger signal in blue. So this is the trigger signal, which is exactly this signal here. And then we have the triggering thresholds, kappa and minus kappa, which is our trigger threshold here. And then, so we start here, the experiment, so we are well within these confidence bounds, and then the green line indicates that we now induce a change. So we simply change the dynamics, and then we want to see, do we detect this change? And as expected, we see the triggering signal to deviate, and then here it hits the threshold, and here we detect, okay, the system has changed, so we then trigger a learning experiment. That's the gray area here. So we do some system identification, get a new experiment, and then we are here. And then green again means we have another change, etc. So what we see then here is that actually here we are quite quick to detect the change. Here we can also detect the change, but here we actually fail to detect the change. So there's a change, but we don't detect it because the signal doesn't hit the threshold. Now, there can be different causes for why we fail here. One is, as I said before, our assumptions aren't satisfied. The change could be too small, but what could also be is that the expected value is simply not fully representative, because the expected value, of course, only captures the first moment of the random variable, so it doesn't capture everything. So therefore, we then went ahead and developed another trigger, which captures essentially the full distribution. So we have the same setup as before, but now instead of computing the expected value of this random variable, we were able to compute the moment generating function. So the moment generating function essentially represents all moments of that random variable and is an alternative way to capture the random variable instead of using the density of that variable. And we show in our paper that we can compute this for the LQR case, where here the omega includes the weighting matrices and sigma is the stationary distribution of the system. So here we actually have system properties represented in the statistics. And then we can use this moment generating function to actually bound the tail probabilities. So these are so-called Chernoff bounds, where we can compute basically the probability of this random variable being above or below certain thresholds based on the moment generating function. And we can then use this to build our trigger to basically say we trigger learning of a new model whenever our random variable is outside of this interval. So again, how does this look like? So to get these bounds, what we can do is we can basically take the infimum here, because S is just is a variable on the right hand side, and then the right hand side depends on this kappa here. So we can now choose a certain confidence that we want, like a small confidence, and compute the corresponding kappa. And then this is going to be our lower bound, and we do the same for the upper bound, and that's how we get the two bounds, and that's how we then build our trigger. And also because of the Chernoff bounds, because these bound the probability of the tails, we already have basically also a bound on the false triggers. And what is good about this trigger is that actually we didn't need an independence assumption, so the autocorrelations are actually encoded in the moment generating function, and also these bounds are actually tied. So let's look at the simulation example again. So it's essentially the same example as before. What we notice first of all is that now the bounds are changing depending on kind of the current model that we have, and that makes sense because, as I said, the statistics of the process are encoded in the moment generating function. So if we have a new model, we expect to have different bounds. And moreover, what we see nicely here is that we can very quickly detect all the changes. So we're much faster than just using the expected value. So we also tried this trigger on simple experiments. So here you see a Furuta pendulum that is being balanced, and then we just slightly tilt this pendulum. So you see here just less than a degree, and here's the corresponding data. So here this is at green is the change, and then we see that very reliably the signal leaves the confidence bound, so we can reliably detect this changed. Of course, there's some transient in here, but we see that the signal stays over here above the bound, so we can reliably detect that change. Okay, so let me wrap up this first part. So what we developed here is essentially event-triggered learning for LQR. So what we have is we have a model of the linear model of our system. We do model-based design, just the standard LQR, and get our controller. And also, based on the model-based design, we can compute the expected cost. We've shown how to do this for the expected value, that's just standard, but we can also do it for the moment generating function. And then in addition, we basically can compute these random variables here, directly on the data and the state and input data, and then we can build these triggers based on the expected value or the Chernoff bounds. Okay, so we've done this for LQR. We are currently also working on extensions towards model predictive control. That's current work in progress, but I'm not going to go into further detail here. Instead, I would like to get to the second aspect that we've developed, where we use this concept of event-triggered learning in a slightly different context, namely for network control systems. And there we're going to use models to reduce communication. That should sound very familiar to most of you who have been working in event-based control and estimation, but then we're going to build event-triggered learning on top of this. Okay, before I get to this, let me first set the stage to talk a bit about what's the problem setting that we are looking at here in network control. So in network control, we're generally dealing with kind of many systems that share a network to exchange data with each other for the purpose of control. Now, if you have large networks with many agents, like here, and now these agents all talk at the same time in a periodic fashion, then this very quickly leads to a lot of data and overloading the network. This in turn means that you will lose data, there will be delays, And also you can consider this as a waste of resources, because in this setting here, the cars are essentially standing still, so they don't actually have anything relevant to tell. Nonetheless, with classical periodic control, they would just talk all the time. And therefore, one main trigger for also this a lot of the work at this conference is to basically develop event-based methods where you only talk when necessary, or where you do only updates when necessary. And we're going to look at methods that do this by using models to predict what the other agents do. So essentially you use a model to predict what the others are doing, and then you only need to communicate when this prediction is off. I'm going to make this precise in a second, but before, let me already introduce a case study or an application that we're going to look at and show later. So this is collaboration that we've done with Thomas Seel and his collaborators at TU Berlin. They're essentially looking at IMU networks for tracking human body motion. So what they do is they equip humans with wireless sensors, like here. These are IMUs that measure that include gyros and accelerometers that measure the motion of the human. And these wireless sensors then transmit their data to a fusion node. That could just be a mobile phone, for instance. And now, because these sensors are battery powered and communication is the main consumer of energy, reducing communication here would mean to extend the battery life. And moreover, also the network has limited bandwidth. So if you manage to reduce the communication by each individual sensor, you could place more sensors. So very clearly here, we want to, it's desirable to reduce the communication in order to fit more sensors and to reduce energy consumption, and thus extend the lifetime of the sensor network. Okay, so this is the main motivation for using then event-triggered sampling, which I guess I don't have to convince most of you in the audience. But of course, the core idea of event triggering is that we don't do periodic sampling based in time, but we basically trigger based on a need. And what we're going to use is we will make model-based predictions. These are in green, and then we will compare like what does the actual data do, and only when the true data, the true signal is off the prediction, that's when we trigger. So this way we will be able to reduce sampling. Okay, so let me explain the core architecture. What we're going to look at here is on the left we have the sending agent, that's a sensor, a wireless sensor, and on the right we have the receiving agent, which could be the mobile phone as the fusion node. And in between we have the wireless network. And now the sensor, of course, observes some dynamical process, and this data is supposed to kind of arrive at the fusion node. But instead of communicating it all the time, we want to be more clever and only communicate when needed. So the scheme that we're going to use is a standard scheme in event-based estimation and control. We're going to first of all use a model of the process here at the side of the receiving agent. And this model allows us to do predictions, which we can then use for fusion or control or whatever we want to do on that side. Now, the model will, of course, deviate after some time from the truth, and that's why we also implement the model here on the sending side. And then we can, on the sending side, compare basically what do we see, what's the true signal here versus what is the prediction. And if the two match, there's no need to actually send anything. But if there's a discrepancy between the actual measurement, the actual state, and the model prediction, that's when we trigger communication, and this is then the event-triggered communication. Now, what I showed here is a standard scheme in event-based estimation, for example, and I haven't talked about event-triggered learning. Now, how does that come into the picture? So, of course, how well we do here will critically depend on how good the model is. So if we have a very accurate model, we'll be able to make good predictions, and we need to communicate very little here. If we have a poor model, on the other hand, the scheme will still work because we're going to detect that the model is poor and then end up sending more often. So then a poor model means we communicate a lot here on this channel. And now our idea is to put actually event-triggered learning on top and basically monitor how often we communicate. So we're going to have a trigger here that monitors how often do we actually communicate, what is the current communication rate. And based on our model, we can also estimate the expected communication rate, and then we're going to compare the two here. And when the two differ, we trigger learning of a new model. And then this model, of course, will also have to be communicated to the receiving agent. So you have temporarily additional communication load, but the hope is that on the long run, this will pay off and you will end up communicating less. So that's the core idea here. We've developed the theory for this, again, for the case of linear systems. So here's again our overview. Now we have a linear model here. The use of the models is now to make model-based predictions and safe communication. So the outcome is communication rate. So as before, we're going to build triggers that now look at the desired outcome, the communication rate, and based on this, decide whether we need to learn and update our model. Okay, so let me give you the details of how we do this. So we consider, again, a linear stochastic system. This time we formulate it in discrete time, in continuous time, even though it doesn't really matter so much. And then what we're going to look at is we have the true system, and we also have a prediction of the system. So a bar is an estimate of the true A, so that's our prediction. And then we look at the error signal Z, that is just the true state minus the predicted state. And then event-based estimation or event-triggered communication essentially works to check this error signal, and whenever that exceeds a certain threshold that we call delta here, that's when we trigger. And the times that this happens, we are essentially stopping times. So we can define the time, basically the time tau as the infimum, the smallest time, or the first time where this threshold is hit. And for linear systems, for these type of processes, we can actually compute the expected stopping time. So we can compute the expected value of when we expect to communicate next. So that's in a sense the expected communication rate or the inverse of that. And then again, we do the same trick. We can have the expected communication rate, and we now can actually look at the actual stopping time. So we look at when do we communicate, how much time is in between. We take the empirical average here and we compare it to the expected stopping time. And then again, we have a trigger. We can say we learn a new model whenever what we observe in experiments deviates from what we expect to see as the communication rate. So again, same story as before. There can be two causes. There can be model mismatch and randomness. And again, we can bound the probability of false triggers here again using Höfting. And in this case, Höfting is okay in some sense because the stopping times are actually IID. That is because we have a resetting property. When we send the state, basically the error gets reset. So the tau I are IID here. And also we can easily bound them because typically in practice you would anyway basically include like a kind of the maximum time when you communicate, or the after which you communicate. So this is also fine. So we've tested this also in experiment. Here's another pendulum experiment where basically we have the pendulum balancing. So the kind of the hitting the pendulum, that's not part of the experiment that you see on the left, but basically on the left is just standard balancing. And what you now see, we're going to put a mass on top. That's just a few grams, and we want to detect this change. So that's what we see here. We basically see here the weight is added, and then we see our triggering signal leaves the confidence bounds. We trigger a learning experiment, we learn a new model, we get new bounds, and we are again well within those. So here we effectively could detect that we add this mass. Now, however, what we found is that there's also cases where things can go wrong, and that led us to then again develop more stronger triggers. So what you see here is a simulation example, and what we plot here is essentially the CDF of triggering times, of the CDF of the stopping times. And we have in blue basically the expected one, and in orange what we see on the in empirical results. And this dashed line here, that corresponds to the mean. So we have here simulation results where basically in this case we actually have a wrong model, and then we see that the mean trigger here is actually outside. So we do trigger based on the mean trigger, and the CDF is also outside. Here's another example where actually there's a match, so we have the correct model and both are fine. But you can also construct examples where the mean trigger actually fails, or the Höfting trigger. So here you will see the CDFs are actually different, the orange and the blue are different, but the mean is exactly the same. So this you can easily construct such examples. So this means in this example the mean trigger is not effective. And that's also no big surprise in a sense, because again, the mean only captures the first moment, but what we really like to do is we capture the full distribution. And that's what then led us to develop other triggers that are based on the full distribution, where we compare the CDFs that are much more powerful. So I'm not going to go into more details here, but instead I want to show you some results on the application case. So here, as I mentioned, we're looking at the problem where we have wireless sensor nodes, and we want to reduce the communication of those sensor nodes to a fusion node. So let me explain what we do. So this is first of all an experiment where we simply have one sensor that sits on the foot here, and then the subject is walking. So this will generate some cyclic pattern here. And then the sending agent, which is just the sensor itself, will decide what data to transmit. And the sending agent will run both the event-based estimation or the event-based communication and the event-based learning. The sending agent will make triggering decisions whether the state and the estimated state deviate, and it will also, whenever needed, estimate new models and then communicate the model. We have further in this application found it useful to extend the concept even a little further and build a hierarchical event-triggered learning scheme. Hierarchical here means that we have two types of model updates. One is a small model update, which is just a dilation essentially of the cyclic pattern. So the model here is essentially just the cyclic pattern of the walking, and the small model update is just the dilation of that pattern. And a full model update would be to estimate a full new walking cycle. And then the receiving agent receives both the data and the new models and estimates a signal from this. So we're exactly in the scheme that I had before, just that we now also have a hierarchical trigger where we decide whether we need a full model updated or a small one. So let me show you some experimental data. So what we're looking at here, this is recorded data. So this is time, and this is here. This is the angle, and then the second plot from up here. This is basically the difference in the angle, difference between true angle and estimated angle. And we put a threshold here of 2 degrees, which is what our collaborators basically said that's the accuracy that they want. So whenever the error exceeds the 2 degrees, let me show this here. So whenever the error exceeds the 2 degrees, that's when we trigger a state update. So that's when we send a data point. And these are the red dots that you see up here. And then on the bottom line, you see our learning trigger. So here we basically estimate what is the probability that the model that we're currently using is the correct one. And we have a significance threshold here of 0.05. If we fall below this, that's when we trigger a new learning update. And what we see up here is essentially here the cycle length changes. So here before there's a longer cycle length, but then the length changes here. And we are able, and this first of all means that the communication rates go up, and we are eventually able to detect this here. And then we do a model update and everything is fine again. Here's a different case where basically there's a full style change. So here basically you see that the style is changing, and then we quickly detect this and do a full model update of this. So if we, the bottom line, then of course we could look at what are the communication savings, and we compare to a periodic baseline of 50 Hertz, which our collaborators told us is already very low. So they would usually go up higher with periodic communication, but of course we wanted to have a fair comparison. So we went very low with the periodic baseline. And then with just event-triggered state estimation, so we do not update models, we could already save roughly 50% of communication. And if we put event-triggered learning on top, we could save more than 70% of communication. And this calculation, of course, includes the additional traffic that we have to communicate new models. Okay, so for this problem of event-triggered, or we have also developed this problem of event-triggered learning for the case of network control systems, where we develop those different triggers based on the mean and the full distribution. And with our collaborators, we've applied this to sensor networks and could already see that we have significant benefits in terms of saving resources. In one of these works, this one down here, we've already started a slight extension towards nonlinear problems. We don't have the theory for that yet, but we've done the estimation basically using Gaussian processes to estimate to estimate new models. Okay, so that brings me to kind of the last part of my presentation, which is going to be brief and give you a little bit of an insight on what we're currently working on. So if we take a step back and think about what have we done in the first two parts, essentially we made decisions about whether two systems are the same based on data streams generated from these systems. So one data stream typically generated from the model, another one from the experiment. And then based on these data streams, we wanted to decide, are the two the same or are they similar, or do we need to trigger a model update? So the underlying fundamental question is, when are two dynamical systems similar? And we would like to build tests for this based on just data streams. And all the theory that I've showed, you've probably noticed, was for linear systems. So of course, extending this to nonlinear is significantly more challenging, and that's what we are aiming at with our current work, where we first start with addressing this fundamental question: how can we compare dynamical systems based on data? How can we build good statistical tests? And in the following, I just give you highlight ideas to give you some idea of which direction we are targeting here. So on the top left plot, what I show you here is basically two trajectories of two Lorentz systems. So these are two Lorentz systems with slightly perturbed parameters. And if I just gave you this data and say, okay, there's the red and the blue data, and ask you, okay, are these from the same system or not? It's not so easy to say. It's not so easy to say whether it's the same or just two different instances, or whether these are actually different systems. And now our idea here or a rough idea that we're following here is that we say, okay, we want to connect trajectories of dynamical systems to probability distributions, and then leverage powerful tests for comparing probability distributions to, in this way, compare the dynamical systems. So to give you some intuition here, I have a two-dimensional heat map of one of these trajectories. So that's one of these trajectories over here, and you can interpret this as essentially asking, okay, what's the likelihood for each place in the state space to be visited by this trajectory? And that gives you this heat map, which then gives rise to a density. And this density is in some sense representative for the dynamical system, and we want to use these densities to compare or to build comparisons for dynamical systems. So the problem that we're essentially looking at is that we have two nonlinear dynamical systems. These are now deterministic, but we're also looking at stochastic ones. So there's different problem classes that we're considering. So we have two of these systems, F and G, both unknown, and we now want to say whether these two systems are the same. And we want to do this based purely on data streams. An alternative could be to first identify the F and the G using some sort of model learning or cis-identification procedure. However, the downside of this is, first of all, identifying such models for nonlinear problems is a challenging problem in its own right. And then once you do this, you also basically have the bias given from the model, because you go through the model to then compare the systems. So what we would prefer is to have tests that operate directly on the data. And as I said, the key idea is that we want to, or for certain classes of systems, a certain class of ergodic systems, we can connect the evolution of the system or the trajectory of the system to probability distribution. So essentially, the dynamical system induces a probability distribution in state space. And moreover, we can sample from these distributions in a sense by iterating the dynamical system. And then what we want to do, or the idea is that we use powerful tests from comparing probability distributions to compare the probability distributions, and in this way compare the dynamical systems. And one way to do this is to use the maximum mean discrepancy, which essentially is a metric in the space of probability distributions. And moreover, using kernel methods from the field of kernel learning, we can efficiently approximate this MMD from samples. So the idea would be to get the samples, compute the MMD, and then basically decide, are the two systems the same or not. The theory behind this is quite involved and includes several assumptions on ergodicity, IID, etc., which I'm not going to go into detail now. But instead, I want to give you an idea of how something like this can work, because we've tried this again on real-world data, on human walking data, to basically detect different subjects, or also whether there's a pathology in the gait or not. So essentially what we did is we took 39 subjects, had them walking on a treadmill, different trials with and without orthosis and different speeds. And here's an example where we see the gyro data of two trials. In blue is one without orthosis, and in red is the one where orthosis is attached to the left knee. So you see here there's some change in the walking pattern. And now what we did, we took this data and did different tests on this. So first we wanted to see, can we detect just from the data streams whether the subject is wearing an orthosis or not? And there we had a very high detection rate, more than 99.9% reliability. We could detect whether there's an orthosis or not. And also we detected whether we can basically match subjects from their walking patterns, because there's usually different walking patterns between different subjects, and this is we also had a high detection rate there of almost 90%. And what is important here that this test directly acts on the raw data, so there's no pre-processing, no feature engineering or anything like this. And that's exactly what we are aiming at. So these are quite promising results, but it's ongoing work. We're developing the theory as well as the looking for further applications of this. But this is quite promising, and this is, I think, a direction how we can extend this to also the nonlinear system case. Now with that, let me actually wrap up and come to the end of my talk. So I've presented the idea of event-triggered learning, and here's again the core concept or the core idea behind this is where we basically look at learning of models and basically consider the goal or the expected outcome of using that model, and then building based on this outcome, build triggers. So we always look at what do we expect to see, what control performance do we expect, for instance, what communication rate do we expect, and what do we actually see in the experiment. And from this, we build triggers with statistical guarantees that then tell us, okay, now is a good time to do a learning experiment. And we've concretely developed this for the case of LQR, as well as for networked control systems so far. And we're now working also on the fundamental question of how do I actually compare our dynamical systems. With that, I'm at the end, but I don't want to conclude before thanking my wonderful collaborators. So first of all, thank Friedrich Solovyov. He's a PhD student and main researcher behind these techniques and ideas. Then we recently had two great master thesis students, Henning Schlüter and Sebastian Schloor from the University of Stuttgart. Henning worked on the event-triggered learning for LQR, and Sebastian worked on extending this for MPC, something that I haven't shown here yet, that we're still about to publish. And then I'd like to thank our collaborators at TU Berlin, Thomas Seel and Jonas Borchert, who was in Berlin at the time. With them, we did the application to the IMU networks, and also want to thank Dominik and Christian from our team, who also made important contributions to some aspects that I presented. With that, I would like to conclude and thank you for your attention. And yeah, I'm looking forward to your questions. Thank you.
Thank you, Sebastian. It was a very, very nice talk. So I think you have some questions. So don't hesitate to raise your hands if you want to give questions. Okay, Marek.
Thank you, Sebastian, for excellent talk. Could you explain me event-triggered learning based on cost of learning? It is the same as learning based on communication, network control system, and trigger based on communication?
It's not the same. So first of all, let me maybe go back to this one here. So the triggers that we develop, we use the same ideas. So basically, we're looking at the random variables that we treat basically the outcome. What I call outcome here, we treat this as a random variable. This could be in the one case the control performance, it could be the communication rate. This is in our setting is a random variable, and then we use statistical results basically to build triggers that give us statistical guarantees. But the triggers themselves, they use similar concepts, but they are different. So in one case, for instance, I mean, just practically the control performance trigger, we basically get the state and input data, we compute our quadratic cost out of this, and this is our triggering signal. For the communication, we basically look at how often do I communicate, like what's the time between two communication instances, and then we take the average. So the triggers are very different. And the concept that is behind is, in a sense, we, as I show here in this slide, we want to look at kind of what do we care about, what do we want to achieve with our model, and we then build triggers based on these. So concepts and some tools behind are the same or similar, but the triggers themselves are then specific to the different problem domains.
Okay, thank you.
Okay, is there some other questions? Okay, I raise the hand. I have a question about your inverted pendulum. In practice, your inverted pendulum, you have already the equation for the control. And if you change the weight of the pendulum, so you put something else on the pendulum, you change, of course, the way it's changing. You change the coefficient in the question, but you don't change really the model itself, right? Is it possible in other circumstances to have a modification of the equation with this approach, or just to change the coefficients?
Yeah, that's a very good question. So in the case that we looked at, indeed, just the coefficients change, but I would say it depends basically on what learning algorithm you use. So you could. So in this case, basically, we just do a new system identification procedure and identify new A and B matrices. Now, whether it's just a number that has changed, or whether, I don't know, a 0 has changed to something non-zero also in the matrix, doesn't really matter to us, because we simply look at, okay, was there an effect on what we care about, on the cost, let's say, and then we estimate new parameters. Of course, it's more, I would say, a question about like, how do you do the learning? I mean, in some of our work, that's work that Dominic is doing, we are also looking at causal learning for dynamical systems, basically asking like, how can I also learn structure of models or dynamical systems, like when the structure has changed. And this, of course, you could imagine that you basically say, okay, you use a learning trigger, you just say something has changed, and then you might want to learn kind of new structure also. But that's more a question of, I would say, how do you do the learning? In principle, you could, I would say, use these triggers also with such approaches.
Okay, thank you. So some other questions, or people wait for the lunch? I think people are waiting for the lunch. Maybe we have to conclude this session. Thanks a lot for this very nice talk, Sebastian. It was a pleasure to chair this session. So just before leaving, look at your emails, because you have the link for the next session, which is also a keynote talk from Yuan Wu. So don't hesitate to join us this afternoon after the lunch. Thanks a lot for being here and attend this session. Bye.
Thanks again for the invitation.
You're welcome.